Hello students, welcome to this lecture on linear prediction of signals. Let us recall linear prediction formulates the prediction y hat n as this is the relationship y hat n is summation hi y n minus I going from 1 to m. Corresponding Wiener-Hoff equations are given by this Ryj is equal to summation hi into Ryj minus I going from 1 to m, and there are m equations corresponding to j is equal to 1 to m. In matrix notation, the Wiener-Hoff equations are given by this relationship. Here this is the autocorrelation matrix, this is the prediction coefficient vector, and this is the SCF vector, autocorrelation vector. So, by inverting this relationship, we can find out the LPC coefficient H1, H2 up to Hm. And similarly, the mean square prediction error is given by that is MMSP, minimum mean square prediction error is equal to Ry0 minus summation hi into Ryi I going from 1 to m. Let us also recall that the autocorrelation matrix of a WSS process is a symmetric Topliss matrix. If we see this Ry matrix, here all diagonal, suppose all elements in this diagonal are equal, all are Ry0. Similarly, if I consider this super diagonal, all elements will be Ry1. Similarly, this sub diagonal will have all elements Ry1 like that, and also it is symmetric. This element is equal to this, like this element is equal to this, like that. So, this lecture will explore the above property to derive the Levinson-Durbin algorithm to solve the WH equations for linear prediction. We will start with forward prediction problem. The linear prediction problem considered so far is a forward prediction problem. This is obvious from the name itself. For the notational simplicity, we rewrite the prediction equation as y hat n equal to summation Hmi into yn minus I going from 1 to m, where the prediction parameters are being denoted by Hmi I going from 1 to m. Here we have included this order parameter m as a suffix. The Wiener-Hoff equations in the matrix form is given by this. This is the autocorrelation matrix, and this is the filter coefficient vector. Here first element is Hm1, then Hm2, like that, and right hand side is the autocorrelation vector Ry1, Ry2, etc. up to Rym, and correspondingly minimum mean square prediction error is given by Ry0 minus summation Hmi into Ryi I going from 1 to m. We will now consider the backward prediction problem. Given yn minus 1 up to yn minus m plus 1, we want to estimate yn minus m. So, what is the best estimate for yn minus m given this data yn minus 1 up to yn minus m plus 1. The backward linear prediction is given by y hat n minus m, that is equal to summation bmi into yn plus 1 minus I going from 1 to m. So, this will be equal to bm1 into yn plus bm2 into yn minus 1, like that. Last element will be bm capital M into yn minus m plus 1. This way we predict y n minus m. We have to minimize the mean square prediction error given by E of E square n, that is equal to E of y n minus m minus summation b m I into y n plus m minus I going from 1 to m whole square. So, this is the mean square prediction error, and this we have to minimize with respect to b m j going from 1 to m. Now, we can apply the orthogonality condition E of y n minus m minus summation b m I into y n plus 1 minus I going from 1 to m. This is the error expression into y n plus 1 minus j, that must be equal to 0 for j is equal to 1, 2 up to m. So, taking the expectation now, we will get summation b m I into r y j minus I going from 1 to m must be equal to r y m plus 1 minus j. So, E of y n minus m into y n plus 1 minus j, that will give us this. So, this set of equation is for j is equal to 1, 2 up to m. In the matrix form, we get r y 0, r y 1 etc. This is the autocorrelation matrix into that backward prediction filter coefficients b m 1, b m 2 up to b m m. This is the filter coefficient vector, that must be equal to r y m and then r y m minus 1 and up to r y 1. This is the autocorrelation vector, but we observe that this is in reverse order. In the forward prediction, it is in the order first r y 1, then r y 2 etc., but here first r y m, then r y m minus 1 etc. Therefore, from the forward prediction problem in 1 and 2 here, we get the relationship between the coefficients b m of I is equal to h m of m plus 1 minus I, where I goes from 1 to m. That means, the forward prediction parameters in reverse order will give the backward prediction parameters. So, this is important observation. These BMIs are nothing but the forward prediction parameters in the reverse order. MMSPE, the minimum mean square prediction error, that is given by E of y n minus m minus summation b m I into y n plus 1 minus I going from 1 to m into y n minus m, that is using the orthogonality condition. So, here remaining terms will contribute 0 because of the orthogonality of the error. This is the error to the data. So, therefore, we will have simply mean square prediction error, that is epsilon m, that is the notation, is equal to E of y n minus m minus summation b m I into y n plus 1 minus I going from 1 to m whole into y n minus m, and this is equal to r y of 0 minus summation b m I into r y of m plus 1 minus I going from 1 to m, and since b m of I is equal to h m of m plus 1 minus I, we substitute this h m of m plus 1 minus I for b m I and we get this expression. And if we carefully observe this equation, it is nothing but the forward prediction error, which is same as the forward prediction error. Thus, the mean square backward prediction error is equal to the mean square forward prediction error. Now, we will go to Levinson-Durbin algorithm. Levinson-Durbin algorithm is the most popular technique for determining the LP parameters from a given autocorrelation data. Consider the Wiener-Hoff equations for the mth order linear predictions. Here, this is the autocorrelation matrix, RY matrix, and this is the prediction coefficient vector HM1, HM2 up to HMM, and right hand side is the autocorrelation vector that is given by ry1 up to rym. And if we write the coefficients in reverse order and right hand side also, accordingly we have to invert the order. So, first rym and then up to ry1. So, that way by reversing the order of the coefficient we get this equation. So, here we consider the mth order predictor, small mth order prediction. Then the m plus 1th order predictor is given by this equation. This is the Ry matrix, this is the H vector and this is the autocorrelation vector. Here Ry matrix is of order m plus 1 by m plus 1 and this is a vector of dimension m plus 1, and similarly Ry is also a vector of dimension m plus 1. Our goal is to express this m plus 1th order predictor in terms of the mth order predictor. Let us partition the matrices in equation 2. We are partitioning by these two lines, so that we have 4 matrices here, this matrix, this matrix, this matrix and this matrix. Similarly, 2 matrices here and 2 matrices here. Now, the Wienerhoff equation can be written in 2 equations. So, first we will multiply this matrix by this vector plus this scalar will multiply this vector, then we will get the right hand side. So, that way this Ry matrix multiplied by this H vector plus H of m plus 1, that is this element, into this vector we will get right hand side, that is from Ry1 to Rym. And if I consider the last row, then what we will get is that this multiplied by this, okay, summation H of m plus I into Ry of m plus 1 minus I going from 1 to m, then H m plus 1 into Ry 0. So, last element H m plus 1 into Ry of 0, and that must be equal to Ry m plus 1. So, because of this partition we get 2 equations now, equation 3 and equation 4. Now, suppose I pre-multiply this equation by corresponding inverse, then I will get this. Similarly, I have to pre-multiply here and pre-multiply here. That way, pre-multiplying both sides in equation 3 by Ry inverse, we get H of m plus 1, H of m plus 2 up to H of m plus 1 m plus H m plus 1 of m plus 1 into Ry inverse of this one Rym minus 1 up to Ry1 is equal to Ry inverse multiplied Ry1 up to Rym. So, that way we have this H m plus 1 vector plus this scalar H m plus 1 of m plus 1 into, now this is if I take Ry inverse into this vector, I will get the filter coefficient in the reverse order. So, that way it will be Hm m, Hm m minus 1 up to Hm1, and right hand side will be Hm1, Hm2 up to Hm. So, what we have observed that this is the m plus 1th order coefficients, they are related to mth order coefficients by this matrix equation. We can write each element like this, H of m plus 1 I is equal to Hm I, this is Hm I from this vector, plus k m plus 1 into Hm of m plus 1 minus I, because it is in reverse order. This is true for I is equal to 1, 2 up to m. Since this is h m plus 1 of m plus 1, therefore, this we will write as k m plus 1 h m of m plus 1 minus 1, because this is m plus 1, here also it will be m plus 1. So, that way we are now able to find m plus 1th order LP coefficients in terms of the mth order LP coefficients, and this is true for only I is equal to 1, 2 up to m. This Km coefficient is called the reflection coefficient or the partial correlation coefficient. Now, from equation 4 we get summation h of m plus 1 I into r y m plus 1 minus I going from 1 to m plus h m plus 1 at point m plus 1 into r y 0 is equal to r y of m plus 1. This we obtain from this equation 4. So, substituting h of m plus 1 is equal to minus k m plus 1, we get this relationship. Substituting for h of m plus 1 I from 5, we have already equation 5, that is the recursive relationship. So, we can write summation h m I plus k m plus 1 into h m at m plus 1 minus I into r y m plus 1 minus I going from 1 to m, minus k m plus 1 into r y of 0, that must be equal to r y of m plus 1. And after simplifying, we will get k m plus 1 into r y 0 minus summation h m at point m plus 1 minus I into r y m plus 1 minus I going from 1 to m, that must be equal to minus r y of m plus 1 plus summation h m I into r y m plus 1 minus I going from 1 to m. So, from this expression we get k of m plus 1 equals to minus r y of m plus 1, this is minus r y of m plus 1 plus summation h m I into r y m plus 1 minus I going from 1 to m divided by epsilon m, where this epsilon m is the MMSPE, the minimum mean square prediction error given by this expression. So, that way r y 0 minus summation h m m plus 1 minus I into r y m plus 1 minus I going from 1 to m. Therefore, k m plus 1 is related with the mean square error, mean square prediction error by this expression. This is one important relationship, that reflection coefficient of order m plus 1 is given by this expression divided by mean square prediction error. Now, the mean square prediction error at order m plus 1 is given by r y of 0 minus summation h m plus 1 at point m plus 2 minus I into r y m plus 2 minus I going from 1 to m plus 1. Now, using the recursion for h of m plus 1 I, we get this relationship. This mean square prediction error also we will be getting recursively. Epsilon m plus 1 is equal to epsilon m multiplied by 1 minus k m plus 1 square, reflection coefficient square. This will be the MMSPE at order m plus 1. Therefore, we will be able to determine minimum mean square prediction error also recursively. Now, this quantity is always non-negative, and since MSE is always non-negative, so from this expression, because this is non-negative, this is non-negative, we will get Km square, that is the reflection coefficient square is always less than equal to 1, implying that reflection coefficient Km, its magnitude will be less than equal to 1. If magnitude of Km is less than 1, the LPC error filter will be minimum phase, and hence the corresponding synthesis filter will be also stable. because here we can ascertain that this quantity is less than 1, so that corresponding LPC error filter will be minimum phase, because we are implementing in terms of Km, and the LPC error filter will be minimum phase, and hence corresponding synthesis filter will be also stable. So, that is one advantage of denoting the model parameters by the reflection coefficients and the corresponding estimation error. Efficient realization can be achieved in terms of Km. Instead of using HIs, we can use this Km reflection coefficient to get some efficient implementation of the prediction error filter, that we will discuss later on. Km is a very important parameter. It represents the direct correlation of the data yn minus m on yn, when the correlation due to the intermediate data yn minus m plus 1 up to yn minus 1 is removed. If we remove the correlation because of this data, then whatever correlation is present, that is measured by E of forward error into backward error divided by Ry0, that is the partial correlation coefficient. Therefore, Km is equal to E of Em Fn into Em Bn, where Em Fn is the forward prediction error, is equal to yn minus summation Hmi into yn minus I going from 1 to m, and Em Bn is equal to backward prediction error, that is equal to y of n minus m minus summation Hm m plus 1 minus I into y n plus 1 minus I going from 1 to m. Now, it can be shown that for an ARM process, this Km will become 0 for m greater than m. So, that way it is a test for this partial correlation coefficient can be used as a test for the order of AR process. So, that we discussed in the earlier class, that how to determine the order of moving average process. Similarly, order of AR process can be determined by examining the Km sequence. Let us see the steps of the Levinson-Durbin algorithm. Given the order of prediction m and the autocorrelation data for m is equal to 0 to m, we initialize Hm of 0 is equal to minus 1 for all m. Then we put epsilon 0, that is the mean square error of the 0th order predictor, is equal to Ry0, and for m is equal to 1 up to m, we do these steps. First, we determine Km by this relationship. So, this Km reflection coefficient of order m, these are determined from the m minus 1th order filter coefficient and m minus 1 order estimation error. And then we will update Hmi is equal to h of m minus 1 I plus Km into h of m minus 1 m minus I. This we will do for I is equal to 1, 2 up to m minus 1. Then we will put Hm of m is equal to minus Km. Because here we have determined up to m minus 1 by this relationship, and since we have determined Km, Hm of m will be equal to minus Km. So, for mth order, all the parameters are determined. Then we will update the mean square prediction error, that is epsilon m will be equal to epsilon m minus 1 into 1 minus Km square. So, that way we will iterate up to m and we will get the prediction coefficients. Some salient points we have to remember: the reflection parameters Km and the minimum mean square prediction errors epsilon m completely determine the LPC coefficients. Alternatively, given the LP coefficients and the final minimum mean square prediction error values, we can determine Km and epsilon m for the sequence. So, this may be required for efficient implementation of the LP error filter. The algorithm is order recursive, because we first determine order 1 LP parameters, then determine order 2 LP parameters, like that. Therefore, the algorithm is order recursive. From the second order LP parameters, we determine the third order LP parameters. By solving the mth order linear prediction problem, we get all the previous order solution. So, if we try to solve the mth order linear prediction problem, we will get the earlier order solutions also. We have to use the autocorrelation function, which is actually estimated from data. So, if the estimated autocorrelation functions satisfy the properties of autocorrelation functions, that is even symmetry and positive semi definiteness, etc., the algorithm will yield stable coefficients. That means corresponding reconstruction filter will be also stable. That is one advantage of a Levinson-Durbin algorithm. Let us summarize the lecture. The forward linear prediction is given by y hat n is equal to summation h m I into y n minus I going from 1 to m. Similarly, the backward linear predictor is formulated as y hat of n minus m, that is equal to summation b m I into y n plus 1 minus I going from 1 to m. So, these are two prediction problems. Applying orthogonality principle to the backward linear predictor, we get the Wiener-Hoff equation as this: summation b m of I into r y j minus I going from 1 to m is equal to r y of m plus 1 minus j going from 1 to m. So, from this relationship and earlier our forward prediction relationship, it can be shown that b m of I equals h m of m plus 1 minus I for I is equal to 1 to up to m. Also, we showed that the backward and the forward mean square prediction errors are equal. The Levinson-Durbin algorithm exploits the symmetry and top-list nature of the autocorrelation matrix of a WSS process. It computes the LP coefficients recursively from the given ACF data in the following steps. First step is computation of the reflection coefficients Km, then updating the predictor parameters HMIs, and then updating the mean square prediction errors epsilon m's. In this way, we can iteratively find out the LP coefficients. Try to solve the following problem. Suppose the ACFs of a WSS process is given by Ry of 0 is equal to 2.89, Ry of 1 is equal to 1.51 and Ry of 2 is equal to 1.21. Find the second order LP coefficients directly by matrix inversion and then by applying the Levinson-Durbin algorithm. Thank you.